record that.
And so 85 doesn't deal with corrosion electrolysis. You should do 85. 85 is just like that methane problem we just did, but a little harder. Because the oxidation is difficult. What else? 88. 88?
Wait, do we do it on now?
No, we're looking at the advanced exercises to see which ones are applicable for this upcoming test. So 85 is. 88, a common reference electrode consists of silver wire coated with silver chloride immersed.
No, not 88.
88 is, yes.
Yeah?
Yeah.
But the ones with corrosion, you said you want to find.
Uh-huh. Yeah. No, you eventually you're going to do all of it, but you don't have to do it because for this coming test for Thursday. On Thursday's test, you aren't going to have anything about corrosion or electrolysis. I don't know if that practice test I did. Oh, look.
Are we going to have that for the final? There's going to be
Yeah, you're going to have it on the final, corrosion and electrolysis. But the final is not going to be heavily biased towards chapter, this last part of chapter 20 or 24 or 25. The final is going to be about like 60 questions, multiple choice, kind of spread over the entire course.
Will we need a Scantron for that?
Yes. I'll bring a Scantron.
Would you say it's really similar to all the previous tests?
Multiple choice, yeah.
Yeah.
The multiple choice questions is kind of similar to the previous exams, multiple choice questions, so it's good to start. Okay. It's only multiple choice. Normally, the thing is, normally I have people sketch out an electrolytic cell. Electrolytic cell. I might have you sketch one out on the final, but the final is going to have some bonus. So the only thing I'd have you sketch out is electrolytic cell. For sure, you're going to have to sketch out an electrochemical or a voltaic cell. Electrochemical refers to both electrolytic and voltaic. So for sure, you're going to have to sketch a voltaic cell for Thursday's test. So there might be like multiple choice problems. Well, I didn't make on this last exam. I didn't make them do a sketch of the cell. Let's see about the other exam.
Thanksgiving bonus.
Well, that was a while back ago. So sketch the voltaic cell using this net reaction.
Would you want the voltage?
The more information you can give me, the more points you get. The less information, the less points you get.
Okay.
So if somebody shows me the voltage and you decide not to, even though you could do it, then you're gonna come out behind. Also, that goes, some people say they take this too literally, so they don't tell me what the anode is, they don't tell me what the cathode is, all that kind of stuff. And other people show me like anode, cathode, everything. And so I want to see everything, as detailed as possible. So maybe I should say detailed. Yeah. So this is a typical question I ask. I don't know why I didn't ask it last year. Maybe I was behind. Not sure. Although this year I'm farther behind. So I'm not sure why I didn't ask it. maybe this year I was probably even farther behind because I combined 19 and 20. But I still have them sketched out in cell.
Mother's Day bonus.
Mother's Day bonus.
We got lots of
Well,
bonuses.
the final exam is going to have a bonus as well. Let's say the Father's Day bonus or the graduation bonus or something like that. And what that's going to be is it's going to be the chemical reactions. You're going to get like 4 of them. This is stuff from the beginning of the semester. You'll predict. Those will be all bonus points.
Perfect.
Like 10% bonus.
Yes, we're taking.
I just pulled out all my old homeworks, like I stacked them up, and have all the practice tests, and here's the I'm not gonna wait till the I hope I pass, because I want to go on to the biggest.
All right. Let's look at the corrosion of iron. Rust is, the corrosion of iron is probably the most important one for corrosion because iron's a structural material. And rust is very common and causes untold dollars in damage every year. But if we look at the corrosion of iron, we normally think iron's just being oxidized by O2. And so normally we would think of it in terms of like a Chem 4 type combination reaction, you know, or redox reaction. Iron solid plus O2 gas, and we just balance it. This is going to yield rust, Fe2O3, which is iron 3 oxide, and then just balance. We need 2 irons and 3 halves in O2. We often write with fractions so that we keep this per mole of product, you know. Rather than multiplying it out, because then it would be per 2 moles of product. So, but it's not this simple. The corrosion of iron is like a miniature battery or miniature voltaic cell. And so even though, yeah, you could write it like this, you know, if we look at the mechanism, you know, how this happens mechanistically, we have to think of it as a voltaic cell, and it's an unwanted voltaic cell because we don't want the iron to corrode. And so if it's a voltaic cell, then the oxidizing agent's O2. There's no acid around. There could be moisture around. If there's acid around, does iron corrode faster or slower if there's acid? It corrodes a lot faster. Because let's take a look at this potential. If we look at oxygen's what is this? Is this is like oxidizing agent, so is this an oxidation potential, or is this a reduction potential? The reduction potential. If we look at oxygen's reduction potential, it's 0.401 volts. This is in neutral solution or basic solution. Well, it's actually got to be in basic because under standard conditions, we need 1 molar OH minus present. And so it's basic solution. This is the potential in acid. And so if we look at the reduction potential in acid, it's plus 1.229 volts. So plus 1.229 volts in acid. Oops. Plus 0.401 volts in base. It's a huge difference. And so that means oxygen is a much more powerful oxidizer in acid solution or in base.
More powerful.
Acid.
In acid solution. Why?
The oxidation potential is higher.
Well, yeah, the oxidation potential is higher, yes. Well, it's not an oxidation potential, is it? Is oxidation potentials used for oxidizing agents? No. We would say because its reduction potential is higher. Yeah. Its reduction potential is much higher. Much higher. Why? Why is its reduction potential much higher?
more negative charge?
Not Le Chatelier's. You know, when we're thinking about chemical reactions, like for example, acid strength, what types of things? We look at the reactivity of the reactants and we look at the stability of the products. And so here, in basic solution, it forms hydroxide as a product. In acidic solution, it forms water.
The bone is stable.
Hydroxide is not stable.
Wants to grab something.
Not stable. What's this hydrogen peroxide? Where is it? It's even higher.
Should be it.
What would you rather have, a cup full of water or a cup full of hydroxide?
Water.
Yeah, water, because they both aren't equal in stability. Hydroxide is very reactive. It's a powerful base. And so, in fact, they use hydroxide, they call it lye, and they use it to clean drains. You know, drain cleaner. But anyway, going back to this forms water. Water is a heck of a lot more stable, so you see that in terms of the reduction potential. The reduction potential is plus 1.229 volts, right? Much higher. There's one more oxygen here. This is oxygen and acid, but it forms hydrogen peroxide, and its reduction potential is a lot lower. You know, it's a lot lower than forming water, but it's a lot higher than forming hydroxide. And so which one's going to form? We have 3 reduction reactions for O2. Which one forms? Well, it depends. Is it in basic solution or is it in acidic? If it's an acidic solution, we have 2 choices. We have this one at 0.695 volts and the other one at plus 1 over 1 volt. Which one do I take?
No, plus one.
The higher one, right? The higher the higher the voltage, the more likely it's to occur. So we completely ignore this one. I mean, this one can occur. Then if we completely ignore this one, then well, then why is this one here? Well, this can occur, you know, under certain circumstances. What about what?
On that slide, you said it was a neutral solution.
Normally we do acidic or neutral. Neutral is very tough because either this is going to have 1 molar H plus or it's going to have 1 molar hydroxide. And so there's really no... In neutral, we have it in the chart. For neutral, it would be non-standard conditions. And these are all standard. These are standard reduction potentials. You know, standard potentials. In the chart, there are 3 or more non-standard potentials, and it's not E naught, it's just E. And put a little asterisk there. And those are for pH 7. Those are the neutral ones, and those voltages are different. None of these are for neutral, and including the one they're showing here. This one has to be in basic solution. If you want the neutral one, we have to change it. It's not this voltage. If we want the neutral one, then we have to compensate for the different concentrations. So we have to do a Nernst type conversion to figure out the one at neutral, that is pH 7.
So it's
This is wrong. Well, it's not wrong. It isn't, in neutral solution, there's no acid or base, right? It's just iron and water. What they're saying is this one's closest, the closest one we're going to use for neutral solution. Because in neutral solution, there would be no hydroxide here. If there's no hydroxide here, would that ink, well actually in neutral solution there is hydroxide here. How much hydroxide do we have? How much hydroxide is there in neutral solution? Let's say pure water.
What?
10 to the negative 7. And so if we go from standard conditions would be 1 molar down to 10 to the minus 7 molar. So we go 1 molar to 10 to the minus 7 molar. What's going to happen to the potential? The potential should go up, down, or stay the same.
It's gonna drop.
So we decrease the amount of product. We decrease the concentration of the product. The voltage is going to drop. No, the voltage increases. If we decrease the concentration of product, Le Chatelet shifts this to the right, the voltage increases. But anyway, this is it. This is the redox reaction here. And so over here we have oxygens, our oxidizer, irons, our reducer, and so the net reaction is this. We're going to form iron 2 initially, not iron 3. And if we have iron 2 and hydroxide, then a secondary reaction occurs here. Iron 2 plus hydroxide yields, iron 2 hydroxide, which is a green precipitate. Iron 2 is green, and so we end up with a green precipitate, which is going to help even further drive this reaction here. But the cell potential for this is pretty high, 0.841 volts. There's a high potential for this to occur. Right? And that is because this isn't so high, but it's not too low. Is that right? How could they add those? Oh, shoot. Huh? It's wrong. This is wrong.
Unless they did the
Reduction potential, it's like reverses that.
Iron
No,
to
that's
iron
the
2.
oxidation potential.
It's positive.
Whoa.
Because
They tried to change the sign but forgot to.
I think, right there.
Yeah. Yeah, the number just doesn't add up. Iron goes to iron 2 is plus 0.440 volts.
But is
Which
it
is
getting
high potential.
oxidized?
What?
But is it getting oxidized?
Yeah, it has a high oxidation potential.
Yeah.
Now wouldn't it be opposite of that?
Let's see. It messed up. They came up with the right answer.
Anyway, Petrucci's getting it. Actually, I don't think Petrucci made this slide anyway. Petrucci actually passed away, unfortunately, but one of his other authors did this. But since we can always blame him because
Can't defend himself.
he can't defend himself. But you know, what is he doing here? Because he loves reduction potentials. Petrucci loves reduction, but he loves to write this iron 2 goes to iron, and then write that. If this was iron 2 to iron, then we have 2 reduction potentials, and then he takes this reduction potential and does a minus of this reduction potential, right? And then it works out. I don't like that. I mean, if this goes iron to iron 2, this should be plus, and then we just add the 2 potentials. So we take the reduction potential plus the oxidation potential. Both are high. We have a high oxidation potential, a high reduction potential, which means our cell potential will be high. And there's going to be a good driving force for this reaction. And this driving force is going to be even bigger because of the precipitation here, which is a stable product. Okay, in acidic solution, we have to change the reduction potential. It's going to be even higher reduction potential, which means the cell potential is going to be even higher. Right? And so corrosion is going to happen a lot quicker because there's a stronger driving force. And usually stronger driving force means quicker kinetics, not always. But in this case it does. It's going to corrode a lot quicker in acid than in neutral or base. So these are the cells. This is just to illustrate the cells that we're looking at. And this is to show the redox reaction that's happening.
Wow, what's that?
Let's take a look at A. This is a petri dish with some salt in here. Oh, actually, do we need salt water? If there's no salt water, the reaction occurs very slowly. So we'll look at it without salt water. So corrosion of iron happens quickly in acid and in salt water, right? But in DI water, corrosion is going to happen a lot slower. So if we look at, we're going to do DI water here. We'll look at A. This is a nail, an iron nail. And the iron nail has been hammered at the ends. And so if you take iron, I think is a BCC, or, you know, I think iron is body center cubic. I'm pretty sure it's body center cubic. If you take iron and hammer it, what are you doing to the structure? You're deforming it, right? When you're deforming it, what you're doing is you're tweaking the positions in the bonds. You're creating what are called defects. And so what we have is we have a lot of defects over in the iron over here, whereas this one was heated and then cooled gently. When you heat something up and then cool it gently, then it has time for the atoms to arrange in a nice crystalline ordered structure. And so this is like pristine iron, relatively free of defects. This is highly defected iron based on smashed structure. And so which one has a higher oxidation potential? The pristine iron or the defective iron? You know? The defective iron has, because some of the bonds are weaker, you know, and those bonds are going to be attacked immediately. It's like a sugar cube. A sugar cube, when it dissolves, does it retain its cubic shape or cube shape? No, it starts to round at the edges. Why does it round at the edges? Because that's where the weakest bonds are. The weakest bonds are at the corner because they're only held together, let's say, by these two atoms. Whereas a face atom is going to be held by a lot more other atoms in the structure. So the more bonding, if this is a corner, we attack the corners first, you know? And so if there's any kind of defect, then those are the atoms they're going to lose first. And so as far as the iron goes, here, this is the cell that we can draw out for this. The cell that we're going to draw out is, what is the anode? The anode of this cell is where the electrons are produced. The anode is where oxidation occurs. And so the iron here, which is the defective iron, is going to be the anode, because this is the irons that are going to be more easily attacked. And so we'll produce two irons here, and then we're going to feed the electrons to the cathode. Well, the cathode is actually iron, and in fact they're both attached, but we have pristine iron. The pristine iron is harder to attack. And so over at the cathode, the oxygen comes in and it's going to pick up the two electrons here. And so we're going to have oxygen plus water. This is going to yield the hydroxide. So how many hydroxides do we produce? 4 hydroxides. So we'll need 2 waters here. I'm going to produce 4 hydroxides. And this has got to consume how many electrons? Not 2, sorry. It's going to consume 4 electrons. So we'll need 2 irons to do that. So we divide this. The cathode is here, and actually this has 2 anodes. There's going to be an anode on the left and another smashed anode on the right. Here. And so what they did was they put a couple of drops of phenolphthalein in here. With the phenolphthalein, we could see where the hydroxide is being produced. You see the hydroxide is going to be produced at the cathode. And so the cathode is the pristine iron, and this is where we're making the hydroxide, and so it turns pink here. Now, if you look carefully at the anode, you'll see a green precipitate coating this. That green precipitate is iron 2 hydroxide. Hydroxide is much less massive than iron 2. So hydroxide diffuses much more rapidly than iron 2. And so eventually the hydroxide diffuses over here and will precipitate out with iron 2. We have to have that. You know, the anions have to migrate to the anode, and the cations have to migrate to the cathode. It's just the cations are too slow. And so this is a slow reaction because space charge develops. If we have salt in our water, then immediately when the hydroxides produce, the cations in the salt can stabilize that. And when we produce the cations over here, the anions in the salt can help stabilize that. So salt water will help stabilize this. Otherwise, we have to wait for the hydroxides to slowly diffuse out here to the iron tube. And so if this were pure DI water, it's going to happen slowly. In salt water, it happens much more rapidly. Okay, this is showing we can create defects by making a kink. Whenever we kink metal, that creates weaker bonds. And so this is going to have 3 anodes. 1, 2, 3 anodes. Same reaction. All right, so these two are just corrosion of iron, A and B. All right, C is galvanized iron. Have you ever heard of galvanized iron? What galvanized iron is they dip it in molten zinc and then they put a zinc coating on it. And so galvanized iron is zinc coated iron. What they did was they just wrapped some zinc film around this. Here. But if we have zinc, what has a higher oxidation potential? Zinc or iron? Zinc has a much higher oxidation potential. And so if we have zinc in contact with iron, then, you know, we don't care about any defective parts of the iron or corners. Corners always attack first. Because zinc is a heck of a lot easier to oxidize. And so here the anode is going to be zinc. So zinc goes to Zn2+. The 2 electrons get transferred to the iron. The iron is going to act as the cathode and feed those to air, O2, which creates hydroxide. And so we see the pink color now over here and here. Now over here you can see a white PPT. That white PPT is zinc hydroxide, ZnOH2. When the hydroxides migrate over here, hydroxides diffuse much more rapidly. And so what this is called is galvanized iron is called, what is it called? It's called cathodic protection or sacrificial anode. Sacrificial anode, the term comes here because we don't care about zinc. Zinc's not the structural material. The iron is the structural material. So zinc is expendable. And so we're going to create a sacrificial anode to protect the iron. The irons are cathodes, so we call it cathodic protection by giving it a sacrificial anode. We can use any metal that's more active than iron to protect it. And so ships, for example, ships are made of iron hulls, let's say, and these are sacrificial anodes that are connected to the iron. And this sacrificial anode is magnesium. Magnesium has a much higher oxidation potential than zinc, even. So magnesium is actually kind of dangerous because it's quite flammable. But it's cathodic protection or sacrificial anode. Anode is where oxidation occurs, so we're just going to oxidize the magnesium. This is easy because once the magnesium is completely oxidized, we just replace it with a new one. And so like if you go to Home Depot, you can buy a sacrificial anode there, you know, for pipe, gas pipes or whatever. So let's take a look at sacrificial anode. This is galvanized iron. If we have zinc anywhere in contact with here, zinc is going to be oxidized first before the iron. Once all the zinc has been completely consumed, then the iron will be attacked. So we just got to make sure we have plenty of zinc. If there are gaps here, no problem. You know, we don't have to completely coat it with zinc. It just has to be an electrical contact. That is, electrons have to be able to move from the anode to the cathode. That's all we need. This is going to be an electrical contact. Another way of protecting iron is to paint it. If you paint it, right, then you're providing an inert barrier. Well, another alternative to painting is copper plating. Copper is very unreactive compared to iron. And so if we use copper plated iron, it will protect the underlying iron until a crack develops. If a crack develops here, then forget it. Iron has a much higher oxidation potential. It's going to be oxidized. And so if you're going to plate it, it has to be completely plated. If you're going to paint it, if there's any chips in the paint, the same thing will happen. You know? An inert barrier is troublesome because it has to be completely sealed in that inert barrier. We can see that here. You know, what has a higher oxidation potential, copper or iron? Iron. So iron is going to be oxidized. And so over here you can see iron is going to be our anode, copper is our cathode. So the oxygen comes over to the cathode, produces hydroxide, takes up the electrons. Iron gets corroded to iron 2, and we see lots of green precipitate here from iron 2 hydroxide. Okay, once the iron 2 hydroxide has been exposed to air, then air is going to oxidize iron 2 hydroxide to iron 3 oxide. And so eventually this green will convert into rust. But it just takes a little bit of time. Okay, any questions on the corrosion? So you should know the terms. The sacrificial anode, cathodic protection. You should know those. And just roughly what it's about. You know, whatever has the highest oxidation potential is going to be oxidized. Whatever has the highest reduction potential will be reduced. We're trying to prevent oxidation of the structural material. All right, the last section of chapter 20 deals with electrolysis. You know, in a normal battery, a voltaic cell, electrons are going to flow. You know, this is spontaneous. This is 1.103 volts. But this battery is rechargeable. So after this battery's gone dead, we can, you know, recharge it. Well, how do we recharge it? We recharge it by forcing the electrons to go backwards in the cell. We force the electrons to go backwards. As long as we apply a voltage greater than 1.1 volts backwards, we can recharge it. And so we're trying to get the reverse reaction to occur. If we look at the reverse reaction, it's copper and Zn2+ goes to copper 2+ and Zn. This has negative 1.1 volts. And so negative 1.1 volts means it's trying to flow backwards, right? But what we're going to do is we're going to put a power supply in there. And so the electrons are pushing backwards, but we're going to use the power supply to force the electrons to stop and then continue to force the electrons to go the other way. And so this is just recharging the battery here. Well, how do we do that? Well, we have to have a power supply. The power supply's got to have some kind of voltage, some potential. So you could use another battery or you could use an electric power supply. An electric power supply is easier because you can just dial the voltage that you want. But the power supply is going to have a cathode and an anode, right? The cathode is where the electrons get sucked in. And so what we're going to do is we're going to suck the electrons in. So we want to recharge this battery. Normally the electrons flow left to right, but we're going to force the electrons to flow right to left. We force the electrons to flow by sucking in the electrons over here. When we suck in the electrons over here, they're going to oxidize something. They're going to oxidize the copper. So the copper is going to go back to copper 2 ions over here. And then the electrons are going to be forced over here. They're going to be forced onto zinc ions. The Zn2+ ions are going to go back to zinc metal. And so we're going to regenerate zinc metal over here. We're going to regenerate copper 2 ions over here and recharge the battery. Does that make sense? And what voltage do we need? We need a voltage greater than 1.1 volts. And so the battery must have, or the power supply must have a voltage in excess of 1.103 volts in order to force the non-spontaneous reaction to occur. Well, sometimes things don't go as planned. Well, you need an overpotential because of the activation barrier on some of these, and sometimes it's tough. So sometimes we'll need more voltage than what you think. And then there could be competing reactions. When you go backwards, maybe different reactions are more likely to occur. And so it doesn't reverse exactly to the same state it was before. Then you have non-standard states, no big deal, that happens all the time. And nature of electrodes. Nature of electrodes is, you know, if you start off with a pristine stick of zinc, are you gonna end up with a pristine stick of zinc when you go backwards, it's gonna be coated with little tiny crystals. And so it's gonna look nothing like what you started with. And so, you know, some of this is not entirely reversible or easily reversible. I have an electrolysis demo I'll bring in after the next break, and you can take a look at electrolysis. But, okay, any questions about electrolysis? That was a 2-cell electrolytic cell. We have 2 types of electrolytic cells. It's 2 beaker system like this. And then we have a power supply. So we got plus, we got minus here. You can force the electrons to go backwards. We could also have 1-cell electrolytic, because this is a non-spontaneous reaction. So we could have a 1-cell deal like this. And so let's, if we look at sodium chloride AQ, this is it. We don't need to, we could just put both electrodes in the same solution. And so over here, the electrons are being sucked. And so what's going to happen here? Well, oxidation is going to occur here. What's going to be oxidized? The species with the highest oxidation potential is going to be oxidized. So what we have to do is we have to inventory this. We have sodium ions, we have chloride ions, and we have water. So out of these 3 species, which one has the highest oxidation potential?
Sodium.
Does sodium have the highest oxidation potential?
Yes, because it has lower reduction potential.
What she's saying is true.
It's wrong, unfortunately. Sodium.
Is it negative 2.7?
Okay, I'll tell you, sodium's oxidation potential is so low that, you know, we'd have to drill a hole through the earth to extend the table down to where sodium should be positioned. Why? Oh, sorry. We have to drill a hole in the ceiling and then extend the table out through the roof up into the sky, and then we can put sodium ions, oxidation potential there. Why? Because this table's not high enough to put sodium's oxidation potential up there.
Yeah, negative 2.7.
Sodium oxidation potential is so low that it's way up there, way above fluoride. Why? We'll just call it very, very low. Because I don't have a number for it. I'm just going to call it very, very low. Why? Wait a minute. I do have a number for it. Didn't I see sodium on this chart?
Yeah, it's right there. I was telling you it's negative 2.7. Maybe not on this chart, but on the other one.
Oh yeah, I do have sodium on this chart. Sodium ions. Here it is. So I was wrong. Negative 2.7.
That's reduction potential.
That's a reduction. Yeah, you're right. That's got it mixed up. It's a reduction potential. It's not an oxidation potential. What is the oxidation potential for sodium ion?
Plus 2.713.
No,
Very low.
no, that's not it, because we call that the oxidation potential of sodium metal. The oxidation potential of sodium metal is very high, plus 0.2. plus 2.7. What is the oxidation potential of sodium ion?
We don't know.
We don't know, and therefore my guess is it's so low, it's up in the sky above us. Because in order to ionize sodium to sodium 2+, we have to remove a core electron. Removing a core electron is going to cost you like 10,000, or 10-fold time. To oxidize sodium to sodium ion is going to cost you, 2,000 kilojoules or something like that. This is going to cost you like 20,000 kilojoules. If this is 2,000 kilojoules, that's 20,000 kilojoules. It's going to be too hard to oxidize sodium ion. Therefore, since it's so hard, that voltage has got to be very, very low. Does that make sense?
Sure.
But we do have the oxidation potential for chloride. Chloride's oxidation potential is very low too, but it's a lot higher than sodium ion, that's for sure. Chloride's oxidation potential is negative 1.358 volts. Negative 1.358 volts. Water's oxidation potential depends. Is the water in acidic solution? If the water's in acidic solution, then it's negative 1.229 volts. If the water is in basic solution, we don't have to worry because it's not there. Technically, this is not right. This is not right because this is not an acidic solution. This is actually neutral. And so because that's non-standard, it's going to be off a little bit. The actual oxidation potential is in our classroom. It's like 0.88 volts, 0.887 volts or something like that, negative.
Wait, about classroom?
Yeah, it's in the chart in our classroom. And, the chart in our classroom has a couple of non-standard potentials, like water. But we don't have the chart in the classroom, and we aren't taking the test in the classroom. And the chart that I'm going to give you is this one. So if I give you this one, we'll just pick the closest one. It's not perfect, but it's close enough. Okay? And so we're going to pick this. Oh, actually, I don't know which one I'm going to pick. Which one is the highest oxidation potential? Which one of those is the highest oxidation potential?
Water.
Water
Yeah.
or chloride?
Chloride.
The highest oxidation potential. No, this was based on number. Which one's higher number? This is different than delta H. If I asked you, and I do this all the time, if I ask you which one's a higher delta H, minus 1,000 kilojoules or minus 1,100 kilojoules, which one is a bigger or higher delta H? Minus 1,100.
More exothermic.
It's more exothermic. Which one is a higher oxidation potential? 1.229 volts, because it's a different reference. This is like Celsius temperature. This is totally different. And so 1.229 volts is a higher oxidation potential. Therefore, this one is more likely to be oxidized. So if we're going to strip electrons by using a power supply, and we just crank up the voltage, if we're going to strip electrons, then it should be easier to oxidize water than it is chloride. Yeah. That's how we do it, except for one exception. Do you know what one exception is? You're always going to pick the higher one, because the higher the oxidation potential, the more likely. The higher reduction potential, the more likely, except for one exception. The one exception is chloride versus water. Chloride versus water is going to have some kinetics in it because of the mechanism. To strip an electron off chloride is so easy. You just take it from the outer shell. So just pull the electron. To strip electrons off water, you have to break bonds and make new bonds. And that has a much higher, what do you call that, hump?
Activation.
That has a much higher activation energy. To strip electrons off chloride has a much lower activation energy. And so, and these two numbers, you know, even though they look pretty different, they're comparable. And so if we have something like this, where we're pulling electrons off, it's much easier to pull, even though it requires more work, a little bit more work initially, it doesn't have that huge bump, the activation energy, so it's easier to strip the electrons off chloride. And so kinetically, chloride is going to be oxidized. So this is the one exception. Otherwise, everything else, you pick the larger. And so we want to pick the larger. This has a higher oxidation potential, but in this case, this is an exception because of kinetics. We pick the one with a lower oxidation potential, chloride. And it's only chloride versus water. Chloride versus water is a special exception. Special exception. All right, then we look at the reduction potential. So what species are we going to reduce? All right, so let's look at the reduction potential for sodium ions. Reduction potential for sodium ions is quite low, at minus 2.713 volts. So the reduction potential, let's do a different color here, minus 2.713 volts. Okay, what's the reduction potential for chloride? Is it higher than sodium ions, lower than sodium ions? What has the lowest reduction potential on this chart? The lowest reduction potential on this chart is lithium ions at minus 3 volts. Is there anything lower than this?
No.
Yes.
Yes, there is.
There's lots of stuff lower than this. It's just not on the chart. One of them is chloride. Chloride is so low we have to drill a hole in the ground to extend the chart, right? So chloride's going to be what we're going to call very, very low. That way we just ignore it because we don't care about the ones with low potential. We want the ones with the highest potential because the highest potential is the one that are most likely to react. Why is that? Well, you could use Chem 1A to understand it. Where does the extra electron go on chloride? If I wanted to try to reduce chloride, that extra electron is going to go into the next, what we call the next shell, next higher energy shell. Z effective is going to be bad. It's going to be unstable. This is not good. And so that's very, very low reduction potential. What's the reduction potential for water? Reduction potential for water, oh, this has got to be the lowest. This is at the bottom of the list. Is that the lowest reduction?